Okay, welcome to 3.4 arithmetic sequences. Up until this point, we've talked about lines and slope of lines and perpendiculars and parallels of lines and everything that has to do with lines and lines and lines and lines, right? Lines and linear equations. We're going to kind of look at this in a different aspect now, something with a sequence. Okay, so let's start with what is a sequence. A sequence is a list of numbers. All right, and yes, it is arithmetic, not arithmetic. Okay, but let me give you some examples of some sequences. We've got 1, 2, 3, 4, ... There's one sequence. Cool. Here's another one. 2, 4, 6, 8, ... There's another one. 2, 4, 8, 16, timesing by 2. That's another sequence. This is one of my favorite ones. 1, 1, 2, 3, 5, 8, 13, ... This sequence is awesome. It's known as the Fibonacci sequence, for anyone who doesn't know that. It is adding the previous two, starting with 2 1s. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. This is the one nature uses a lot. It's super cool. Anyway, it's the sequence itself. There's a lot of sequences. Basically anything that has a pattern. Okay, any list of numbers that has a pattern. And it really doesn't even have to be numbers. We're focusing on the number ones, but sequences could have shapes. You could have emoji sequences. I don't know. You can do whatever you want. We're going to focus on stuff like this. Arithmetic sequences means an adding pattern. Okay, now it doesn't have to be adding positive numbers, as we will see, but we're going to focus on those ones. We're going to step away from the multiplying patterns. We're going to step away from the adding the last two together. Technically, that's adding, but like here, the first one is adding 1, the second one is adding 2, right? Starting with the first term. Okay, now we're going to find a lot of this is very, very similar to linear equations, but it does have its own terminology, so we're going to take just a minute to kind of figure out what this terminology means. So, A is our sequence. We're going to list a sequence as A. If we have a second sequence, it's B. If we have a third sequence, it's C. Whatever your sequence is named, the individual terms of that sequence have that same letter. So if we're going to use 2, 4, 6, 8, then this would be A1, A2, A3, and A4. And what it's just saying is the first term, the second term, the third term, the fourth term. Okay? For a term number we don't know, then we would use n. So n, think of it like the place value. First place, second place, third place, fourth place, fifth place, right? So if 2 is the first term, then n is 1, but a1 is 2. Okay? So a is referring to the actual number sitting in that place, where the little subscript, the little n, that's going to be the place value. So it is the first, the second, the third, the fourth. All right, cool. Then we're going to talk about something called explicit versus recursive. And each of them has their own formula or their own equation. We'll dive into those really in the examples because I think they're easier to see on an example than they are just to talk about. But those two things are something you also want to know. All right, let's go. Example 1.1. Complete the sequence using recursion. What are the 5th, 6th, and 5th, 6th, and 10th terms of the sequence? Okay, let's pretend it didn't say with recursion. We're at home. Our super old aunt just gave us one of those really classic like picture puzzle books, right, for Christmas or whatever, and we're bored out of our minds. So we decided to open it up. Maybe we're humoring her and we're doing one of the puzzles, right? And this is a puzzle, and it says, okay, find the missing pieces. And you're like, all right. Or maybe you're sitting at a restaurant and you're just playing with your younger kids or your younger siblings' kids menu, right? And it has, okay, fill in the blanks. This is a fill in the blank. How do I fill in the blank? Here's my first blank. Second blank, third blank. How would I figure out what goes in A5? Well, I'd have to figure out the pattern first, right? The pattern here is pretty important. Otherwise, I don't know how to fill in the blank. If I know that it's supposed to be an adding pattern, and even if I didn't, I could figure it out. How could I figure out what is it adding by? Well, how do you go backwards from adding? Subtraction. So how do we get from 5 to 9? 9 minus 5 is 4. How do you get from 9 to 13? Oh, 13 minus 9, also adding 4. 13 to 17, yep, I added 4. Okay, so it looks like each time they're adding 4. Sweet. This pattern is what we call the common difference. Now you would think it'd be called the common sum. If it was me, I probably would have called it the common sum because it's adding, you know. But the difference, I think, comes from when you're subtracting 9 minus 5. There's a difference of 4 between them, right? A common 4 between, anyway. It's a whole thing. But we call that common difference, and we use a little d. So d is equal to 4. Great. The pattern is adding 4. Sweet. So now how do I find A5? I am going to add 4 to A4. I'll just keep going. A5 would be 17 plus 4, and that would be 21. Okay, so A5 is 21. How am I going to get A6 now? Oh, I'm going to add 4 to 21. We're going to keep going with the pattern. I'm going to use A5, the previous term, and I'm going to add my common difference to it, 25. Now, hopefully, if I add 4 to this one, I get back to what A7 is. If I add 4 to that one, that's 29. And yes, that's the next one in the pattern, so we know we're right. Now, this idea of taking the fourth one and adding 4 to it, and then taking the fifth one and adding 4 to it, and taking the sixth one and adding 4 to it, that's called recursion. Okay, think reoccurring. It's just reoccurring over and over and over again. It's counting. It's counting by a pattern. Your most basic of patterns, you're counting numbers. 1, 2, 3, 4, 5. This pattern, 5, 9, 13, 17, 21, 25. You're counting by 4s. Okay, so reoccurring over and over again this pattern. It's not a super, like, fancy, it's basically a fancy word for something that's not so fancy. So, using recursion again, let's find A10. Well, to do that, I got to go back one term, 37, and add 4 to it, which would be 41. Cool. I found them all. I should probably box all my answers. Now, these don't have labels. Okay, if you want to put A5 equals 21, A6 equals 25, that'd be helpful, but we're just finding term numbers. Awesome. Okay, so these notes are designed for class, the videos aren't designed to, like, you can skip out on class, but so normally we would take a time and I'd have you do example 1.2 on your own. So go ahead right now and pause the video. Try 1.2 on your own. If you need more than, or no, you can pause your video. I'm going to basically go really fast through this next one. So go ahead and try it on your own and see if you get it right. Okay, hopefully you had time to pause the video. So here, the common difference, we can see adding 5. And so A5 would be 5 plus 23 is 28. A6 would be 33, and A7 would be 38. Not super bad, right? All right, cool. 1.3 is actually a different type of pattern, and it was in there by a mistake, so we're actually going to cut it out. We're going to skip that one, and we're going to go to example 1.4. 1.4, hopefully this isn't even in your notes, honestly. Hopefully 1.3 doesn't, like, I'm going to fix that before I photocopy them. So hopefully it's not in there. If I forget, though, 1.3. That pattern is not adding, so we're not going to deal with it. Not that you couldn't. I mean, you're totally capable of doing it, but we'll do it later. All right, example 1.4. Find the ninth term of the sequence given by an equals 3n plus 1. Then graph the first 5 terms of the sequence. Interesting. This is no longer a placemat, you know, kids, what's it called? Like kids word search, kids menu kind of thing, right? It's not a puzzle anymore. It's an equation. But this equation is going to give us the sequence, okay? This equation may look familiar if I maybe replace this with this and this with this. Hey, I know those things. This looks like slope-intercept form, but we'll get back to that. Think of it that way. But what we're going to get, the solutions we're going to get out of this are a sequence. Okay, so let's find the first 5 terms first. Maybe that'll help us. No, let's find the ninth one. Ninth one's not too bad. So ninth term. What does that mean? Well, if I need to find the ninth term, that means I need A9, right? Now, if I compare that little symbol to the little symbol in the y's place, what has changed? What has changed is n has become 9, right? It's no longer just some random n, right? It's not some any place value, kind of like y is just any number. It has now become a very definite 9, ninth term. I need the ninth term. Well, if I'm doing that on one side where I'm replacing n to 9, why don't we just do that on the other side? Let's make all the n's 9. And then I will get my 9th term. So this is basically just finding a solution given part of the solution. We're basically back in 3.1. 27, 28. 28 is the 9th term. Sorry, my 9 looks like a 4 and it's bugging me. There we go. Nope, that's really ugly. Anyway, you're fine. So A9 is equal to 28. Now this is what we call an explicit formula. Meaning, explicit, obvious, and fast, and explaining, right? It's explaining what's happening in the pattern, first off. That's kind of where explicit comes from. But it is the one that will generate a single term. Okay, it's just going to be spitting it out. Explicit's really convenient when you're trying to find the 9th term and you don't have any of the first terms, right? It is even convenient if you do have the first one, but you don't want to sit there and add this, add this, add this, add this, add this, all the way up to 9 or 102, right? If I asked you to find the 109th term and I gave you the sequence and I gave you like the first 5, y'all would hate me because you have to sit there and add whatever, like how many times, right? So explicit is great if you want to skip terms. Think skipping terms. However, we don't necessarily have to use it. If we want to graph the first 5 terms of the sequence now, we can use it to maybe find 1 or 2 and then just use recursion. Okay, because to find a lot of terms, explicit is a lot of work, right? Think if I gave you like 5 solution problems to solve for one equation. Well, that's a lot of equations to solve. So recursion is also very helpful. We don't want to use one or the other. We want to know kind of both. But we kind of have to start with the first one. I need to know what the first term is. A1 would be 3 times 1 plus 1, so A1 is 4. From here, I can do A2. I might want to do the first 2, so that way I can kind of see what the common difference is, not 21. That would be 6, 7. Okay, so it looks like the pattern is adding 3 each time. Now, if you remember way back from freshman year where you first taught this, the slope of this explicit formula is going to be your common difference. Okay, so this is the common difference. But it's very important that this is not your first term. We always relate that to the y-intercept because it's so easy to do that. So I hesitate to say this is going to be exactly like linear. It's got a lot of similarities, but that one is not the first term. Okay, that's not your first term. Notice I plugged it in. My first term was 4. Technically, it's a y-intercept, but remember y-intercepts go with 0, and having a 0 term doesn't make any sense. So we can't just say that that's the first term. Okay, we can't just make life that easy on ourselves because the math doesn't work out right. We can be as lazy as we want, but the math's got to work. Okay, so I have the first 2 terms. Now I know the pattern is add 3. So I could plug in 3, I could plug in 4, and I could plug in 5, but instead, why don't I just add 3? A3 would be 10, A4 would be 13, and A5 would be 16. You see how easy that is? So recursion came in handy here when we had to find 5 terms, whereas explicit was helpful when we only had to find 1. All right, then we'll graph them. I'll do a teeny tiny graph over here. Here's my n, here's my an. I hope you can see some similarities there, right? An. I hope you guys don't mind my handwriting on this thing because this stylus is donezo, ready for the garbage. Okay, term numbers 1, 2, 3, 4, 5. There we go. And then, let's see, it's going up by 3, starting 4. Let's go by, I need to get to 16. Let's go by 5s. 5, just because I have no room here. Okay, 5, 10, 15. Okay. All right, 1 is at 4. 2, nope. 2 was at 7, 3 was at 10, oops. 7, 10, 16. Okay. Now I'm not going to connect these dots. Okay, if you remember our conversation the very beginning in 3.1, how a line is a connection of all possible dots, right? And those dots have to fit the equation. But to fit to this structure, you would say that having an n of 0.5 makes sense. Now, this is kind of a domain thing, but don't instantly shut down when I say that. Does having half a term make sense? I can't have a 0.5 as n because n is supposed to be a place, right? A first, second, third. We don't have a halfths place, right? That's even weird to say. Or a 3.5ths place. Like, what? Are you not half, like, are you half a term here? That makes no sense. So by connecting those dots, remember you're drawing all the dots. You're not just drawing a line, you're drawing all the dots. And so you're saying that all the dots exist. And all the dots don't exist. So we want to be very careful about what we're trying to say here. So this graph has no connection of these dots. It's very explicit. Alright, cool. The next one is very similar, but unfortunately there's a typo, so we're going to go ahead and change that. Here, this makes no sense. We're going to change that. AN equal to AN minus 1 plus 2 and A1 equals 3. Sorry, that's what it should have said. I don't know how it turned into that. Whatever. Okay, very, very, very similar situation, except they didn't give us an explicit. They gave us what we call a recursive equation. The recursive equation looks like this. But it's the same idea. I have a recursive equation, and I need to find the 7th term, and I need to graph the first 5 terms. So, what does this recursion equation say? It says the first term, which is very convenient. It says A1 is equal to 3. There's the first one. Sweet. Now what does it say about A2? About A squared, A2, not A squared. Very important difference. A2. A2 here is going to be made by taking A1 and recursively, or reoccurring, getting to the next one. So how would that work? How would I figure out what they want me to add a common difference from the previous one to the next one? It tells me right here. This looks a little crazy, but this n minus 1 is just a subscript. Okay. AN and AN minus 1 is the same thing as Y2 and Y1. Okay, it's just one less than, right? If n was 4, AN minus 1 would be 3. If n was 3, then n minus 1 would be 2. If n was 15, n minus 1 would be 14, right? So in this case, if n is 2, n minus 1 would be 1. So A1 plus 2, would be 5. So my next term, it looks like I'm adding 2 each time. All right, cool. Now A3, add 2 again, add 2 again, and add 2 again. And we used recursion to find the first 5 terms of the sequence. Technically, the 7th isn't that far away. We could use recursion there too. So why not? Let's go use recursion. A6 is equal to 13, and A7 is equal to 15. Cool. We found it. It's 15. Now let's say we didn't want to do that route. Let's say it didn't ask us to find the first 5 terms of the sequence. They just gave us the recursive equation though. Well, I could make the explicit equation. Making the explicit equation isn't really that bad. It isn't even really that different from the slope and y-intercept, right? They gave me the first term. The first term, okay, so AN is equal to D n minus 1 plus A1. Notice how similar, yet not, this looks to a linear. I've got a y, a slope, an x, and a y-intercept-ish. Okay, now it's an ish. We did just talk a lot about the fact that that's not a y-intercept at the end, but it's taken care of now by this. Because it's not a y-intercept, I'm just subtracting one from the x, quote-unquote. If you follow me on that, great. If not, just commit this thing to memory so that you can plug into it. So AN is our y, so it'll stay AN. What was D here? Oh yeah, we figured out that we're adding 2 each time. So D was 2, n minus 1, plus our first term was 3. So our explicit formula is this. Or if we simplified it, 2n minus 2, right, distribute that 2, we would get 2n plus 1. 2n plus 1 would be our explicit formula. Okay, and then the 7th term, we plug 7 into that. Oops. And we would get 2 times 6, which is 12 plus 3 is 15. We get the same thing, right? So if we hadn't been asked to find the first 5 terms of the sequence so we could graph them, that excuse me, then we would be able to just jump straight to an explicit formula and be able to solve it. So something linear that we could plug into, right? Finding a specific solution. Okay, I'm going to leave you guys to graph this one if you want to. We're going to move on to kind of reiterate these ideas. Okay, 2.1. Find the common difference, write the explicit formula, and find the 10th term for the following sequence. Okay, here I have a sequence. What was the common difference again? Oh yeah, that was D. That means I'm going to figure out what the pattern is, right? So let's figure out the pattern. All of 2.1, 2, and 3, try out on your own. Like, try all 3 of those before we really get into this, because honestly, it's the exact same stuff we just did before. I'm going to give you a chance to. Okay, now let's breeze through this real fast. 3 to 9, that's 6. Looks like D is equal to 6. And so our explicit formula, oh, and A1 is equal to 3. And so our explicit formula would be AN equal to 6n minus 1 plus 3. That's kind of uggo though, so let's clean that up a bit. 6n minus 6 or 6n minus 3. Okay, and now we're going to use it to find the 10th term. So A10 be 6 times 10 minus 3. 60 minus 3 is 57. Follow your PEMDAS, people. Make sure you follow your PEMDAS. All right, if that was too fast, it was the exact same thing as the last one. So if you have any questions, write them down, come see me. Next one, write the linear function that corresponds to the arithmetic sequence. So first we're going to need the explicit formula, because that's very linear looking. So let's go ahead and find that. Interesting, this one has a subtraction pattern, and you might not think that means it's arithmetic, but we're really just adding -7 here. So it's not the biggest difference, it's still an adding pattern, we're just adding something that is negative. We can't do that little trick with multiplication or division or anything like that, but this is kind of a little trick for subtraction. Okay, so that means AN, our D would be -7, and our first term would be 8, and then -7n plus 7 plus 8, -7n plus 15 is our explicit formula, but then a linear function we kind of already saw at the very beginning. I said we're going to come back to this. Just sub out the variables. Okay. Now these graphs would not be the same, right? The graph of the y equals -7x plus 15 has no restrictions of it not being a place value, right? This would just be a straight line. Solid, infinite number of responses, bunch of dots all put together. The other one, this would be the dot graph, right? Because n can't be a half, n can't be 3/4, n can't be -5, right? That makes no sense. N is first, second, third, fourth, fifth. So it has to be your counting numbers. Whereas this one could be a straight line. But you can see that creating the equation, the difference, not that bad. Okay, 2 more. An arithmetic sequence is defined recursively by this guy here. Maybe we'll underline that. It's always a good idea to underline those things. Find the first 5 terms of the sequence, write an explicit formula, and then find the 15th term. So this is basically what we did in the 1.5 there. Let's go ahead and try it again. First term, we found it, or they gave it to us. This recursive here is telling us that the previous term, n minus 1, adding 5 equals the next term, an. And sometimes it's easier to see that if you just simply switch the equal sign around. An minus 1, the previous term, plus 5 gives you the next term, an, right? So that means A2 would be plus 5, 34. A3 plus 5, 39. A4 plus 5, 44. And A5 plus 5, 49. There's the first 5 terms of the sequence. Notice that's really easy to do when you have recursion, when you have a recursive and you know that pattern, right? Okay, now explicit sequence. Well, we found that difference. We have the first term. So AN equals D n minus 1 plus A1, which is our linear, right? It's y equals mx plus b, but it has been adjusted so we don't have a 0, right? So the x is n minus 1. All right, and that would be 5 n minus 1 plus 29. Clean that up a little bit. 5n minus 5 plus 29. That would be an equals 5n plus 24 is the explicit formula. Okay. And last, we will use that explicit formula to find the 15th term. So an equals 5 times 15 plus 24. Oops. Come on. 5 times 15 plus 24 is 99. Whoops. Yeah, you guys saw I play Pokemon Go. Hit me up if you ever want to play. Come on. Alright, that would be 99. Oops. Oh, okay. One tiny thing. I made a boo-boo here. I left that as n. I need to make sure I change that to 5. 15. A15 is equal to 99. Alrighty, so those are kind of 3 try on your owns, which is good. Let's do one more now, real world context, because why do we care? Right? Like, why do we care? So we care because we want to know if we're going to make money. Money is fun. You are trying to save money so that you can buy a new tablet computer. Is tablet really a computer? I don't know. This tablet costs $450 because it's apparently some weird knockoff brand. Your grandparents give you $50 for your birthday. Before that $50 gift, you didn't have any money saved because you stink at saving. You have a babysitting job and plan to save $10 each week. Write an arithmetic sequence to represent the scenario. In how many weeks will you have saved enough money to buy the tablet? Okay. Whoa, that's a lot of information. When it comes to chunky word problems like this, or really any word problem in general, we kind of talked about how math is a different language, right? And so we need to be able to get this into something we've been talking about. Now, where we're headed in this section is pretty easy because it's math class, right? And we're talking about arithmetic sequences right now, so we know that an arithmetic sequence is going to come out of this. In fact, it even says to write an arithmetic sequence. However, that's not a real world skill. Okay, if I'm in the real world, I don't know what I'm using. Okay, I don't know, but translating is the biggest life skill you could have, man. And this is honestly kind of why people make you take math. It's because they need you to translate things. You would think we'd make you take Spanish, but no. Translate, solve, and translate back. Now, when you're in the real world, solve, translate back. Solve can include things like Google. That's okay. You can solve with Google. You can solve things using the internet. And you can solve things using your friends and using your books and solving however you need to, okay? That's why we have notes. Please use your notes. Notes are important. Use them. But if you have no idea what the question's even asking, you can't Google it. That's the whole point here, people. Are you going to remember the quadratic formula 5 years from now? Probably not. You may not even remember it now. But are you going to remember how to translate something into something that can be solved? I hope so, because that's the thing that people pay for. If your boss, sorry, I usually relate it to business. If it bugs you that I'm doing business, think of your own example. But if your boss walks in and says, we're losing $400 a year on this, this, and that, you need to solve it, go. You need to figure out what the heck you're supposed to do, right? You're trying to figure out, okay, is he asking me to save $400? Is he asking me to fire people? Is he asking me to cut things? Am I supposed to come up with a plan? You need to translate him. Your boss just rattles off a bunch of stuff you don't know and you can't translate it, you're going to end up getting fired. Because he doesn't have time to translate for you. He doesn't have time to spell it out. If he did, he would do it himself. So translating is this huge skill. Being able to figure out what people want from you is like one of the biggest resume aspects you could ever have. Okay, and people who can do this really successfully get really far in life. Like really far. And it's so applicable to every job. Being able to, if you want to run your own business, you want to just be your own boss. You don't even want to have a boss. You need to figure out what your customers want. You need to figure out if your customers want, when they say, well, I want the blue one, and you have 47 blue options, you need to figure out how to translate that into what you want, right? So just being able to translate is one of the biggest things. So if you can translate by the end of this, I'll be super happy. The end of this year. All right, let's translate this, though. So tablet costs $450. By the way, if I ever go off on a rando speech in the video and you just want to fast forward it, go for it. I will do that in class and you have to listen to me, but it's okay. Your grandparents give you $50 for your birthday. Before that, you had no money saved up. Don't really care about that. Plan to save $10 each week. Hopefully by now, someone has shown you underlining a word problem. But if you truly and honestly hate underlining a word problem, then don't underline a word problem. You're an adult now. Do whatever makes sense to you. If you need to pull that information out and write it on the side, go ahead and do that. If you need to cross stuff out because you don't like to look at the other stuff, that's fine. But find a way that works for you so that you can whittle this problem down into like short tidbits of information, okay? For me, that's always underlining because I'm lazy as all crap. So, all right, write an arithmetic sequence. Well, now I need to translate this. So I have the $50 from the birthday. I have $10 a week, and I have $450 total, and that's all. Okay, so what does this mean? So arithmetic sequence, what do I need for that? I need arithmetic sequence. Those missing pieces are N, A-N, D, A1, yeah. Okay, so I need to come up with something like that. So this sounds like a first term to me. I'm going to call that A1. This is me translating. I am translating this into the math class we have been talking about. $50 or $10 a week sounds like a pattern. So I'm going to call that D. And then I don't know what to make of this. Yeah, I don't know that yet, so I'm not going to translate that. Which is okay, because all I need is to write an arithmetic sequence. So A1 would be 50. D is 10, so that means the next one would be 60. Next one would be 70. 80, and dot, dot, dot. Now we're an arithmetic sequence. Fabulous. Now you could argue this sequence does, terminate. It does end. But then you could also argue that, are you really going to stop saving? Are you going to quit your job right after you get the tablet? Maybe if you're smart, you won't, right? Maybe if you were solely like, this job is for the tablet, and once I get it, I'm done because I want to go back to my friends. Like, you could say it's 450 cutoff. If you kept the job, you probably just keep dot, dot, dot. That part's up to you. But key point here, it goes up by tens. Cool. There's our arithmetic sequence. Now we need to figure out how many weeks until we can get that tablet. Okay, so here's where this comes in, right? And notice my line of thinking right now isn't clear and concise, and it isn't step 1, step 2, step 3. The teacher is muddling her way through this. Do you see that? This is real life. I am muddling my way through this problem. I'm going step by step and I'm like grabbing ideas as they come to me. It's supposed to be messy. Okay? Highly recommend you're organized so that in that case you can keep track of your thoughts, but more often than not, they're going to go all over the place, and that's okay. It's okay. I recommend a good eraser and not pen. Okay, but $450 total. Let's see. That sounds like an answer. So $450 sounds like a term, right? It was our term in the sequence. And so we need a number of weeks. Looks like N would be the weeks. Okay, so N is going to be the weeks. So I need to make a formula. I could do this one of two ways, actually. I could keep counting until I hit 450. But that seems like a lot. So maybe I'm just going to come up with like a little like equation to solve real fast. Let's do 10. N minus 1 plus 50. Okay, yeah, because I can solve that real fast. 450 equals 10 minus 10 plus 50. That would be 60. Oh, pardon me. It's 10n minus 40 plus 40. Subtract, that'd be 410 equals 10n, and so 41 is equal to n. And then quick translate back, 41 weeks. Because if your dad's like, hey, how long is it going to take you to buy the tablet? You're like, n equals 41. Dad's going to be like, do we need to go to the doctor? No, it's 41 weeks, right? You got to make sure you translate back into English because you don't talk in math. Okay, that is arithmetic sequences. And really, at the end of the day, they're all about word problems because the word problems, really, we deal in sequences a lot more in real life than we do in linear equations. But they have so many of the same aspects that they're easy to convert back and forth. All right, if you have any questions, as always, shoot me an email or a Canvas message. I'll answer pretty fast. Or come see me in person. Have a good day.